Everybody, I hope you are ready because we have the final talk of today's session, the PRISM online seminars. If you wonder what PRISM means, it means payload and research investigations in satellite missions. And satellite missions refer mostly to the NSPO's satellite missions. So therefore, most of the talks will be geared towards the scientific and technical questions, issues related to the third space plan, national space science plan. And of course, one of the important elements is the FORMOSAT 7 missions, which is doing a GNSSRO. And here's we have a Professor Charles Lin from National Cheng Kung University, who's an expert on the atmospheric application of this radio occultation data. Charles, please start.
Yes. Okay. So thank you for introduction. So I will try to keep in time. Okay. So I will talk about the geospace dynamic. The reason I use the Geospace is recently astronomy colleagues like to use Geospace. It looks more fancy, I think. So this work is contributed by my co-authors from NCKU and NCU. So I would, because COSME 2, FORMOSAT 7 COSME 2 is a follow-on mission of the FORMOSAT 3 COSME 1. So I will talk about the history. In case some of you are not aware of the why atmosphere community think these radio occultation observations are important. So I would elaborate that. So before we start, just do the atmosphere 101. So atmosphere in Earth, atmosphere is mainly around 100 to 1,000 kilometers in altitude, and most of the atomic oxygen plus ion and the O2 plus, NO plus, and helium and hydrogen and helium, and so the atmosphere is filled with plasma that disturb radio waves, and all our satellites from FORMOSAT 1 to FORMOSAT 7 right now are actually all in the atmosphere. So not long ago, I heard people saying that, oh, we are finally not doing the atmosphere science in our satellite mission. I found that kind of bizarre because it would be weird to say, forget about atmosphere in our mission. No, you have your missions there, right? You cannot ignore it. So what I show below here, the red line, around 250 kilometers, is a red line emission visible line. It's mainly from the atomic oxygen ion excited, and that emitted the red lines. Below, you see a very thin layer of the a green line. That's a 557.7. It's also from atomic oxygen, and it's an edge of a space around 90 kilometers. And below that, from 80 to 50 kilometers, you see a yellow lines. Those are the sodium metallic ions from brought in by the meteorites. And way down, you see this is Taiwan. Okay, so it's kind of interesting to see this. This is like a traditionally we don't think we see the plasma. This is really show you how the plasma looks like. Okay, so way back ago when people started to do the atmosphere since World War II, most of people observe the atmosphere using the radars. So on the left-hand side are the ionosomes. The principle of ionosome is that it transmits the radio wave. And when the radio wave frequency matches with the ionosphere plasma frequency, it reflects back down so that we can know that the altitude of the ionosphere plasma frequency. In that way, we are able to observe the bottom side or a half of the ionosphere below the peak. Once it goes above the peak, the radio wave either refract, and when you go over it, it transmits it, it transpasses it. So, so the only way you can observe ionosphere from the ionosome is you only see half of the ionosphere. If you want to see the entire ionosphere, you have to use big radars. which is on the right-hand side, is incoherent scattering radar, ISRS, which transmit very powerful radio wave to check all the electrons and ions in the ionosphere to let them emit EM waves. And you use a huge antenna, as you can see here on the top is a Millstone Hill radar's antenna, and Arecibo radar's antenna, and the Hikamaka radar's antenna. That huge antenna collect those emitted radio wave and to derive the ionosphere for the entire profile. Okay, so I would say, so this is a traditional observation, right? So in the later slide, I will show you why, well, I'm sorry, I just didn't follow it quite well. Ionosphere is part of the thermosphere and part of the upper atmosphere. That means what we did for the weather forecast, straightforwardly can be done for the same way for the space weather, right? But why people say that not until you have a FORMOSAT 3 COSMIC 1, right? And then after we have a COSMIC 1, people will say, oh, we also need a FORMOSAT 7 COSMIC 2. Maybe, I mean, after this talk, you will find that I would say you also need a FORMOSAT 11 COSMIC 3, perhaps. Yeah, it would be great to have it. Okay, so as I mentioned earlier, that those are radars see half of the ionosphere or big radars, and recently they are also very powerful tool by using the ground-based GPS receivers. There are more than 6,000 ground-based GPS receivers are open data to public to everyone. So in that case, on the left, you see the GPS transmit signal to the ground receiver, and when you measure the phase shift of the received signal, you can derive the electron content along the path. But what you can do is you can only get the integrated electron content. So GPS sees widely, but you only have a 2D observation. So traditionally, they are observations from here I show on the right below ISRs. So very few. They are roughly only 10, and they don't operate every day. And they are ionosomes. They are also roughly 50 to 100, but they have some difficulty for the data analysis. Some of them are real time, but as you can see, they are very sparse around the world. And as I mentioned about the ground-based GPS receiver represented by the blue triangle, open triangles are around the world, and it's actually much denser than what this figure shows. But you see there's no observation over the ocean. And the green dots are the radio occultation from the FORMOSAT 3 COSMIC 1. So on the left, you see the principle of the radio occultation that receive the signal from the GPS and when going through all the ionosphere and atmosphere. And larger proportion of the radio goes through the ionosphere. And on the middle over here is a derived electron density profile. So this is what we can get, and we are dreaming of, because as I mentioned that there are hundreds of, roughly 100 ionosomes only see half of the ionosphere, and there are around 10 ISR that operated sporadically that can see the entire. And you have a GPS TC observation only get a integrated of this electron density, but you don't see everything. Okay. Okay. So knowing that the occultation can provide this kind of a global coverage with altitude, so it's really see widely and 3D. So let's go back to ionosphere. So why does ionosphere matters to us in Taiwan? So if you look at the upright figure, if you are an alien from other planet, and you happen to come to over nearby the solar system, and you look at the Earth from the space, what you see the light are most prominent are the aurora and the two aerial bands around the equatorial region, and these are the equatorial ionization anomaly, the strongest electron density in the ionosphere. So you see the two bell of the brightness, okay? And actually from here, you can see the lights are not continuously, suggesting that they are irregular structure inside, okay? And why we call this is equatorial ionization anomaly, well, when we talk about this, people will say, oh, this is not usual. but I'm telling you that this is a usual day. This anomaly appear every day. The reason it was named as anomaly because it only contracted to the theoretical prediction. So the name was given by that, but it's actually the everyday structure. And as you can see below, here are the time satellite. There's a instrument called GUVI observation of eagle, showing the equatorial anomaly as in the image as a two belts, and Taiwan is located beneath one of the north equatorial ionization peak. So it's right above us. That's why that's important. So I briefly talk about how it is formed. The EIA equatorial ionization anomaly is formed by the equatorial plasma fountain effect. When there's a eastward electric field in this cartoon plot, that would interact with the magnetic field. So in the equal speed direction, that bring the plasma going upward. So it's like a fountain. You have equal speed to bring the plasma up. And then those plasma are diffused down along the magnetic field line and they accumulate at the two low latitude region. And that's why you have a stronger electron density of the equator than the equator. So this is a simulation, shows that the electron density distribution in respect to altitude and latitude. You see two EIA peaks at the low latitude, and on opposite in the equatorial region, electron density is weaker. Suppose if you look at the traditional theory, that solar UV ionized plasma, the peak should be at the magnetic equator, but the reality tells us that the stronger electron densities of equator at the low latitude. On the right-hand side are the plasma fountains. Why I'm showing this is that all these were not observed before the COSME-1, FORMOSAT 3 COSME-1 mission. So until we have a FORMOSAT 3 COSME-1 mission, we are able to, like I mentioned earlier, we are able to gather these electron density profiles a lot in different latitudes. Here are from the high to low latitude equatorial region and to an opposite hemisphere in the high latitude. This is early data for the FORMOSAT 3 COSME-1 at 2006. So at the time, we are able to average 40 to 20 days of data to plot the ionosphere slice in altitude and latitude, like I show here. So this plot shows the 100 to 500 kilometer overplotted with the magnetic field at different local time from 01 to 23 in respect to latitudes. And you will see that how the ionosphere grow and the equatorial anomaly produce, and there's a symmetry, and then they dies out when they goes to after sunset, post-sunset time. So this was a GRL paper when we have the COSME-1 observation. It was a surprise because people see all this kind of picture the whole time, and when we submit the paper to the journal saying that, well, what we see the whole time are models, not the real observations, and kind of reviewers agree with us because they look back all the knowledge were from the models, and there are some observations, but the observations are like at certain latitude, certain altitude, certain time, but you don't see this kind of thing before. But the witness is that this has to average your data for 40 to 20 days. So they are also challenging for us that saying that, how do you take into account the day-to-day variability? But at the time, day-to-day variability of ionosphere was not thought to be important. Until now, people know that it's very important. So theoretical models suggest that the ionosphere looks like this. If you organize every data at the same local time globally, because the ionosphere is highly local time dependent, so you have to organize data in the global constant local time to compare the longitudinal effect. There are some longitudinal effect at this peak electron density and the height of the and the height of the peak electron density. So above are the number density of the peak electron density, below are the altitude of the peak. Okay, and there is some longitudinal variation, but it's rather smooth. compared to reality. This is the reality, the peak altitude of the peak electron density, and the peak electron density itself, and the total electron content, all measured by FORMOSAT 3 COSME 1. And it's in the, at the time, because the satellite were not separated, so we kind of binding 2 months of the data to get this kind of plot, and it shows this altitude and latitude distribution of it. So that time was quite exciting that we able to see the structure we've been studying for a long time in realistic way. And then, because we have that tool, right? So it's kind of a, you want to see more, right? It looks very, from this figure, you see it's very dynamic. It's the large variations in longitudes. So you wonder what happened if you see further. And at the time, there's a big discovery, but it's not studied by us, but studied by the, I'll just show this figure first. It's discovered by the scientists in UC Berkeley, Space Science Lab. They used the image satellite. Image satellite was built to look at the aurora, but it happened that in some position they are able to look at the low latitude atmosphere. So they are able to see the EIA belts. So they collect all the data for the low latitude region and put together the data in the equinox, March equinox, to construct the map shown in the bottom. It shows that there's a 4-peak structure, and that match with the dashed lines. Dashed contours are the atmosphere tides. The tides, atmosphere tides, propagating from the tropopoles to the lower atmosphere, lower thermosphere region, and they are well matched. Okay, but for this figure, they kind of only have a one hemisphere observation, and the other hemisphere observation is kind of projecting the real observation to the south hemisphere. So they actually have one hemisphere, and they only have one local time because of the orbit characteristic of the satellite. So in the time, we are able to look at this structure by looking at the FORMOSAT 3 COSME observation of the density, electron density, and we construct this map. This is to compare with the image satellite, so it's organized into at the same local time, at 20 local time. And it's interesting, you see these peaks are matching with this lightning rich region. And lightning rich region are the region where the tropospheric convection is strong. When the tropospheric convection is strong, there are more water vapor. Water vapor would release the latent heat. That's the main source for generating atmosphere tide, responsible for this kind of structure. Okay, so I've been talking to people saying that, okay, what I showed earlier in the previous slide, that the terrestrial weather, the weather at the surface can affect the space weather. What I get the feedback is, it's not wow. No, people will say like, well, you know, this is kind of a straightforward to us, right? They are all part of the atmosphere, and well, and it's denser down below for the surface weather. They are much more atmosphere density than above. So it's straightforward. It will affect above, of course. But if you talk to the atmosphere scientists, they will say no, that's not true, right? This is one of the figure I took from the EOS cover for the stratosphere southern warming study. It shows that there are a lot of turbulence at the mesopole region. So at the mesosphere to the lower thermosphere region, because of a very sharp temperature gradient, and it's super cool at the mesopoles. So there are a lot of turbulence over there. So these turbulence are disrupting those waves and tides from below. So traditionally, people would think those gravity waves generated by even tsunami, volcano, or earthquake, or thundercloud would not go to the upper atmosphere because they are all disrupted by this mesopoles turbulence. And of course, the tide has a longer wavelength, but it's likely they will also be affected by it, right? But the previous observation showed that no, right? The ground troposphere distribution, troposphere convection has a same location as those ionosphere peak electron densities. So it's really a big discovery. So the paper of the UC Berkeley group, when it was published, almost everyone, every astronomy scientist in the world are looking at those waveform structure in their data. So I think their paper quickly gets like 400 citations. Okay, so I should move faster. Okay, so here's this picture from that. So from below is a precipitable water vapor. This is derived from FORMOSAT 3 observation, and it has a connection with these lightnings. Okay, and it also shows the waveform structure in the thermosphere temperature at 110 kilometers. This is accumulated 60 days of observation of the time satellite. Then FORMOSAT 3 observation becomes so valuable. It gives you the distribution of the waveform structure at certain altitude, and it also shows you that you can compare here when you have the trough, the EIA, how EIA looks like, and when you were on the peak, how EIA looks like. Okay, so this is really the picture become clear that the lower meteorological effect would be seen in the atmosphere, in the space. And things become crazier. So I will show later. So this is just another view that we are providing this three-dimensional structure of the electron density in the atmosphere. Okay, and now people tend to use the variation of the atmosphere from the FORMOSAT 3 to validate their model. So for example, here you will see the wave 4 or wave 3 structure are different for different months from January to December. You see the wave 4 as September, but you actually see the wave 3 in December. And do they match with the time satellite observation, or do they match with the model? So very quickly, cosmic observation, FORMOSAT 3 cosmic observation are used to test if the whole atmosphere model has a correct output or not. If it has a correct output, it should produce an atmosphere similar to what FORMOSAT 3 observed. Okay. And things become crazier is that we were talking about the equatorial weather affecting the equatorial space. And starting from 2008, people talk about the stratosphere southern warming. So this is again, this is a cosmic FORMOSAT 3 observation of the stratosphere temperature. Remember, for the FORMOSAT 3 cosmic, the orbit goes to 72 degrees. So you can also look at some of the high latitude atmosphere and ionosphere. So here are the atmosphere at the around roughly 30 kilometers. And you see that the 2009 on day 14, still a cool temperature over the polar region, and gradually this cool temperature being eroded by this warm temperature area, and it starts to show the wave structure over here: cold temperature, warm temperature, cold temperature, warm temperature, and then later the warm temperature takes over, and it's become all cool. So this is a stratosphere southern warming, and you will later produce the Arctic oscillation that will eventually affect the weather in the ground. So people are seeing this stratosphere southern warming SSW affecting ionosphere, not at the high latitude, but at the equatorial ionosphere. Okay, I'll just show you that how the temperature goes. The 2009 one is the very large one, and the temperature goes up very rapidly. Temperature increase, and then gradually goes down. So this is from the Koncharenko et al. 2010. They are from the MIT Millstone radar group. They observed that if the normal ionosphere shows the morning, this is 15 UT, roughly 10 local time in the American sector, then the equatorial anomaly start to build at become strongest at 16 local time, which is 21 UT. This is a normal day structure, and during the SSW, you will see that the early morning enhancement followed by the afternoon decrease. So if you take the difference, that will be like here. It has a morning increase followed by the afternoon decrease. So there are questions, what caused this? Are they only happen in the American sector? Do they happen everywhere? And what's the driver for that? At the beginning, people don't believe that the SSW in the polar region can affect the equatorial ionosphere until one simulation paper tells them that there's a non-solar synchronized tide can be produced during the SSW. So people use that as a mechanism to explain that. But for the problem for theory is that when it's non-solar synchronized tides, atmosphere tides, that will be only occur at one region. If it's a sun-synchronized tide, that will occur at everywhere globally. So to test it is simple by looking at the FORMOSAT data. So I'll just show one example over here. We use the FORMOSAT data to run the density. So we do the peak electron density difference between the pre-SSW and SSW period. So here you will show that this is a time sequence for different local time. From above is earlier to the later. It looks the same. Oh, okay. So on this one is a peak density difference. Here are the density difference at 300 kilometers. So both show you that the enhancement is really in one particular longitude, but decrease is global wide. So this decrease is likely produced by the sun synchronized tidal effect. Okay, so so this is a summary of what I've discovered. Well, there are a lot of discovery of the electron density by the FORMOSAT. I'll just pick up two most important ones. One is the wave-form structure, the other is the SSW effect. And you might notice that I've been talking about space weather. I'm talking about space weather affected by lower atmosphere effects. I have not been talking about magnetic storm, those energies from the sun. The reason is that when the COSME FORMOSAT was launched at 2006, if you look at this is a solar flux along since 1945. So you see all these 11 years of a solar cycle, right? And you see the Apollo mission to the moon was launched during the relative lower solar activity cycle. And when the COSME 1 FORMOSAT was launched in 2006, it's really reaching another very small solar condition. It's even, if you consider all the way until 2012, it's even still smaller than the cycle 20, where the Apollo mission was operated. So there's not much of a storm. So first reason is that it was under very low, extremely low solar activity at the time. Second reason is that what people normally show you how many observation points from the FORMOSAT COSME 1 is kind of an illusion. They put all the data for one day. So what I showed earlier, the green dots are from 24 hours of data. So I'll give you a number for the meteorological weather forecast. So every 6 hours, they assimilate 4 million of a data set, 4 million data set. For the ionosphere, for the real-time data we have, is 20,000 per day. So this is our number, okay? And then if you count that, okay, if FORMOSAT gives you 3,000 soundings per day, and you divide it by 24 hours, that would be roughly 100 something points per day. So if you look at this figure, the red triangles are from the ground-based GPS stations, and blue dots are from the FORMOSAT. And if we accumulate data for 3 hours, it will be like this. It's insufficient to complete the global three-dimensional structure as what I showed earlier. So what I showed earlier are all 20-day or 40-day average of observation, But for the magnetic storm effect, it's really, you have to look at the day-to-day variation of the data. Okay, so one way to solve it is to build what people do for the meteorological weather, is that you build a data simulation model. So we have one that's mainly built by the Professor Koichi Chen, Jiahong Chen, and that he's working very hard on this physical-based thermosphere ionosphere data simulation model and has a good result. And it will use a theoretical model. It's very time-consuming, and along with a ensemble common filter. And we have a lot of help of the ensemble common filter from Professor Su Ziyang. But this is kind of a more complicated system. And we have another solution that is using the Gauss-Markov data simulation, Gauss-Markov common filter data simulation. This is done by the Dr. Qian Lin, I'm sorry, Qian Lin, and this the main paper was published in JGR 2007. Excuse me. So if we do what the right figure shows, that we assimilate all the occultation total electron contents. We assimilate the entire ray path into the model using the common filter. Here, X is a model updated. It can be a simple empirical model update, tells you what the ionosphere looks like in the next time step. And so this is kind of propagating ionosphere from one time step to the other. And there's an error covariance. Error covariance responsible for the, at one grid point, you see your relationship to all other grid points. So that if you don't have observation at this grid point, you can still update your status if other grid point get updated. And then by using that error covariance, you can also be updated. So error covariance is extremely important for the common filter approach. Then the forecast is corrected by the observation. This is observation difference, observation model difference, and the adjust by the common gain. Common gain is updated of the observation operator H, convert the observation to different observation to the model, and then empirical model to convert the observation geometry to the I'm sorry, not the empirical model, converted the geometry from observation to this forecast X, and then you update this common gain every time step. By doing so, we are able to produce this kind of electron density structure three-dimensionally, and every hour, by use like every hour, every day. So now we don't need to accumulate 20 days of data. Every hour we get this kind of global structure of the electron density. So here the red arcs are the occultation locations of the FORMOSAT 7 cosmic 2. The yellow lines are the orbit of the FORMOSAT 7, and the green dots are the ground-based GPS observations we use. So from this, we are able to produce this map. And okay, so initially the model, the data are taken from model, but after a few time steps, the data is totally away from the model. It's really become the data-driven one. And the high latitude ionosphere are really given by this ground-based GPS observations. So what I'm saying that it's good to have a FORMOSAT 11 cosmic 3 is that if you look at this figure, most of the observations are in low latitude region, where still you need the information from high latitude, because you need to know high latitude. High latitude and mid latitude is in connection with low latitude ionosphere, because they are all constrained by the magnetic field line, right? So they need to be connected. So it would be good to have observation for also mid and high latitude, like the FORMOSAT 3. Okay, so as I mentioned earlier, that once we do that, we are able to see day-to-day variation. So this is an example for the FORMOSAT 7 observation. So 2019, August 1st, at 400 kilometers, 300 kilometers, 200 kilometers. And again, this red red arcs are the geometry of the observation of the FORMOSAT 7. And on the next day, and you see for the August 1st, electron density has a stronger number density at the lower, at the later local time, but become earlier the next day, and then going back to the later, and then going back to earlier. So you see like a 2 days period of the appearance of the structure, and this kind of thing was not seen before, and we find that this is one important thing. And all these data are available for the FORMOSAT 7 database in the TACC, and also from our side in NCKU. So they are all open for public to be used. So use that. We now really can look at the magnetic storm. So I'm showing you one example. So we're kind of lucky. We see this event 2 months after, 1.5 months after the launch of the FORMOSAT 7. So you see the minor magnetic storm here at August 5th. So on the left are the high latitude radar observation of the convection, showing that the cross the cross polar cap potential drop, indicating the current flowing in and out from the solar wind. And on the right are the solar wind parameters. Solar wind velocity goes up to nearly 700 kilometers per second, which is not very impressive. And IMF turns southward for sometimes for more than 5 hours. And then from that, you can derive the electric field. And then also the magnetic field perturbation observed at the equatorial region. This is a DST. This index is used for indicating the strength of the magnetic storm. So for the superstorm, this can go to minus 300 or minus 500. The most extreme one can go to minus 1,000. So this case goes to only minus 50. That tells you this is really almost nothing. This is a minor magnetic storm or category 1 hurricane or typhoon. Very weak one, but produce a very strong effect. So here we show you that at different altitude from the data product of the FORMOSAT 7, 300 kilometer to 60 to 20, and from 4 UT to 14 UT. And you see gradually when the storm hits after 8 UT, the storm hits after 9 UT, and you will see the enhancement of the equatorial anomaly region, but also the enhancement at the European region. You see a relative strong enhancement compared to the pre-storm hour, and that intensified quickly to produce what you see at 12 UT. Also the 12 local time at European sector. And also you see a strong enhancement over the India. And that goes away for the low latitude 2 hours later. But for those in the European sector still remain strong. Okay, if this is a number density difference at different altitude. If you look at the percentage difference, then you are surprised that you see 300 to 800% of increase for different altitudes since 10 UT to 14 UT. And those at the European sector is like it can be 800% difference compared to the pre-storm condition over here. And normally this kind of thing would not occur until it's a superstorm. So this is an event for the October 2003 Halloween superstorm, right? It produced this global ionosphere map, show that I just need to mention that this is an oversimplified global ionosphere map built by 150 GPS stations. So you see rather smooth structure over here. So you see a pre-storm condition, storm day condition, and this electric field produces a super fountain effect. And this is one of the historical magnetic storm effect. And I just let you look at this first. So you see electron density. This is from model result for the event. Electron density for that historical Halloween storm produced a 140% increase and 130% increase. But look at the milestone in August 2019. It goes as large as more than 270%, and somewhere it even goes to 300%. And I would like to mention to you what these percentages are based on the peak to peak, not the peak to normal. Okay, not based on the location, but based on the peak to peak. So peak to peak, this is some areas like more than 3 times or 4 times the increase. And so again, because we have the 3D structure, we can see the pre-zone day electron density distribution in respect to altitude and attitude. On pre-zone day and under zone day, you see the symmetric EIA has occurred, and then you can try to guess what happened by looking at this structure, variation of this structure. Okay, so this is one from the sun. Finally, we are able to do the magnetic storm effect. Okay, so I just need to. Okay. So next, this is also happened in 2019. So it's kind of lucky that we captured 2 unique events in the year of the satellite launch. So in that year, it's very rare we have the Antarctic SSW, Antarctic stratosphere southern warming. That has a 60 K of the temperature increase. It's only the 3rd time in the history that documented the Antarctic SSW. And it's the strongest in the history for its rapid temperature increase. So Yamasaki et al. Reported the temperature increase as shown in this red line. And then this is a aurora and MLS observation of the wind pattern, long-zone wind pattern in respect to altitude and the time. As you see that the wind gets a reversal. This is an indication of the SSW occurrence. So we plot the cartoon here. It's like, when the SSW occurs, it looks like this planetary wave or Rossby wave become clear that weaken the polar jet and the warm air able to go out. And that affect remotely to the low latitude ionosphere and globally, actually for this event globally. So previously, what I say about the SSW effect is that it produces a low latitude ionosphere has an EIA occur earlier and become weakened after. But for this event, it does not produce that effect. It produces a 6-day wave oscillation, 6-day oscillation of the, so we call that as a quasi 6-day wave, Q6DW. So this is if we organize the electron content observed by FORMOSAT 7 along with time and longitudes. Okay, vertical is a time, day of year, and horizontal is a longitude. And if you remove the background, you see there's a periodic variation. And if you use a tidal fitting to fit out the 6-day wave amplitude, and you see the amplitude of the 6-day wave over here. And if you plot in the amplitude of the 6-day wave, now we put the longitude on the vertical and horizontal at the time, and overplotting with the temperature of the stratosphere in Antarctic, you see the temperature increase and the amplitude of the 6-day wave intensify. These are the 6-day wave oscillation in the ionosphere. And we are able to look at the amplitude of this wave in, again, in the electron content over here. And overplotting below are the temperature of the stratosphere. And this is a total electron content variation, and this is a percentage change. Roughly, it produces 20% of the ionosphere electron content variation, which is the biggest one compared to all other 6-day wave. Like every year around the equinox, there are 6-day wave, but normally the amplitude would be less than 10%. But for this event, this 6-day wave has a more than 20% of the amplitude. So, and these are the fitting of the particular 6-day wave type with a certain wave number and propagation. So I'll just go to the next slide. That will show that if we plot out the strongest day, the day with the strongest amplitude at day 270, 2019, in respect to magnetic latitude and local time, you see this peak occur at around 10 to 12, and another peak around sunset hour. So if you look at the absolute value, it's not very straightforward because the ionosphere always have to compare with the background. So if we look at the relative amplitude, you will see that the two peaks has a strong relative amplitude in respect to the background ionosphere. So traditionally, what people can observe the 6-day wave oscillation is only at around 14 to 18 local time. For this event, it produced another peak at 10 to 12 local time, which is different from previous. And also, this was the paper published by a student working with me, Dr. Jiating Lin, in GIL 2020. So as I mentioned earlier, that this is most prominent 6-day wave that we ever observed. So if we look at the density, it will be like this one. Normally, the 6-day wave oscillation only give you 10% of the ionosphere electron density variation. So if you look at the raw electron density without doing any filtering, you won't see the 6-day oscillation. But for this event, you can see it, okay? So for example, here, September 27, 2019, you see this electron density at 400 kilometer altitude. Taiwan is over here. 3 days later, intensify, and 3 days later, decrease. And this was not seen in other 6-day wave oscillation event. This is in comparison with this one. And this is how the stratosphere vortex become like. This is from the MERA satellite observation that shows that when the stratosphere southern warming comes in, you have this wave number one planetary wave in the polar region, and that produced this 6-day oscillation. Okay, so I've been talking for a very long time of how ionosphere change during the solar storm or the lower atmosphere effect. I want to briefly talk about why it's important to the real application. I'm sorry, I'm kind of a talkative. I've been talking too much. So I'll try to make this clear and quick. So this is a cartoon. It shows you the ionosphere cartoon plot of the cosmos and the plasma bubble here and ionosphere and the GPS satellite. Okay, so if one use this application to receive the GPS signal, so GPS is used by measure the distance from the satellite to the user. By knowing the distance between user and the satellite, for 4 satellites, you can derive your location, your position, okay? But the ray path is not going straight. Rather, it's affected by the ionosphere and atmosphere. So actual path would probably go by this yellow line, but when you receive it, you don't know that they already been banned. So you saw that this is the actual distance between you and the satellite. And so you saw that and you shred it, and then you got your position way wrong. That you have a wrong position because you get the wrong distance. This is the idea. So we want to know that how much of the ionosphere density over here that distort the wave path. And why this is important is that there's music goes out that for the aviation, which is the main space weather user, that they want to use the GNSS or GPS to guide the airplane while they are flying and while they are taking off and the landing. So the idea is that right now you need to use the ground instrument to guide us airplane to land or take off, but they want to use the ground-based GNSS receivers to broadcast the information, and there's no ground instrument needed except the GNSS observations. And the reason is that right now use the ground instrument is that you actually have your airplane go in a distorted way, bending way, because you want to aim in the ground instrument on the runway. And also when you are flying, you have to go along with these ground stations. But if you use a GNSS, right, you know your position of the airplane, and the towers, control centers know your airplane's position the whole time, so that they don't have to go along with this ground station. They just only can go directly, straightforward. So you'll be like this. You see so many flights on this left-hand side. How many flights today? I mean, this is before pandemic, okay? So what happens is that from the right figure over here, if the ground-based GNSS on the airport telling you that there's no atmosphere threat, but indeed airplanes are under the deep atmosphere threat, so the information given will be wrong, okay? And this is particularly important if you look at the below figure. For example, on the right below, you see there's a strong density from the east coast of the US, and that will propagating westward, okay? So airplane in the central US flying over the east coast, the tower at the east coast will say, okay, we have a strong density, strong atmosphere threat, you need to correct it. But the airplane is actually situated at a location with no threat. Or the other way around, the towers is in the Central America, planes at the East Coast, and they will have an opposite effect. So this will be important to know this. So that's why Space Weather Focus Center are chosen not by the Weather Bureau, but by the ICAO, International Civil Aviation Organization. Okay. Also by the self-driving car. So I see this. This is a self-driving car from Stanford University. You see they put 2 GPS receivers to correct the atmosphere, and you see there's no one in the driver's seat. Also, my car has the auto self-driving effect mechanism, but it's not very good. So here you see that on my instrument board, you see that it tells you the speed limit is 110. Okay, it's on the highway, but actually highway is on above. I'm actually down below waiting the red light, but my car, so that I'm on the highway and supposed to go 110 kilometers per hour. So this is a problem, okay? The other problem would be the plasma bubbles. I haven't talked much about it, but it will be important for the FORMOSAT 7 costing too. When there are a lot of irregularities in the atmosphere, it will scatter out the signals, and it will be like this. GPS signal goes through this plasma bubble, and the signal become noisy and even loss of lock. So receiver cannot lock the signal and would lose the reception of the signal. So, and that would be a problem. And the irregularity comes from the equatorial plasma bubble, and it's produced by this Rayleigh-Taylor instability. That's the principle of that when you put lighter things below the heavier things. So magnetic field holds the denser plasma above, and that if you something being disturbed below and you produce these irregularities, and this is altitude versus longitude. And when the plasma bubble goes up, it's tended to higher latitude. So it's always along the field line, and it goes up, and it's tend to higher latitude, and it will be like this shape. Okay. And I'm showing you one example that our Oscar image observes this plasma bubble propagating eastward. The bubble always go east and north, okay? And when this bubble comes over Taiwan, GPS, these are the GPS stations, observation of GPS signals. So we have roughly 150 stations over Taiwan. And then when you see these blue dots are the loss of signal being disturbed. Okay, so the positioning cannot be good under this condition. So one thing I want to talk about is that internationally we now have 3 prominent satellite missions. One is by ICON. ICON is proposed by UC Berkeley team because of wavefall structure, and GOLD is proposed by scientists originally from Florida State University. It's now moving to University of Colorado at Boulder. And ICON ICON and the COSMIC 2 has the one same instrument. It's the ion velocity meter, and the COSMIC 2 FORMOSAT 7 can see the plasma bubble radial scintillation from radial occultation, and it has IVM, it has RF beacon to look at the irregularities and plasma drips. And the goal, as I show over here, goal is on the geostationary orbit, taking the image of the UV. So this is a UV image of the taken by the gold. So all others are the radio waves or in situ density measurement. Gold is like the ICE, it's a remote sensing satellite, but it's not looking at the visible line, it's looking at the UV band. And you can, UV band can see the plasma structure at 300 kilometer well, and you see these stripes are the plasma bubble structures. So combine these three, I think we should move on. So for the FORMOSAT 3 COSMIC 1, so this is also some of the FORMOSAT 7 observation is much denser than FORMOSAT 3 for looking at the bubble. So what I want to say is that for the FORMOSAT 3 COSMIC 1, we able to know better the global atmosphere structure and then improve it and build a data simulation model. We want to do more challenging things by be able to predict or forecast the plasma bubble, which no one can do it right now. As you see on the right-hand side, the simulation of plasma bubble, you see how much dynamic in this structure is. It's a nonlinear structure, and then because we have a lot of plasma bubble observations on board the FORMOSAT 7, so we think we should do it. So I just like to use it. We're doing it because it's difficult and it's interesting. So I think this will conclude my rather lengthy talk. Thank you for your attention.
Yeah, thanks, Charles, for this very detailed and you would say lengthy talk. Because I know that you told me you have to go to pick up your daughter, but maybe you have one question, one question. Anyone want to ask Professor Lin a question before he goes away?
Yeah. Maybe people are.
No, I mean, you did not mention that the one thing that you always want to say is that how important is this observation? I don't know, it's that important to B5G,
Yeah.
And you forgot about that. You want to talk about for another half hour?
No. No. But I think if you look at this slide that
okay.
then you will see that. Yeah, you will see that if the signal being affected by it. So this is for the L band. B5G has the L band and the Ka band and Ku band. So for the L band part of the B5G can be affected by this plasma bubble effect, I think.
Yeah. Okay. So maybe you could next time you spend more time on this single slide. That's important for our colleagues.
Yes.
Doing B5G.
Yes. I hope I will have another talk maybe next time. Yes.
Yes, we will do that.
Yeah.
And you kept on saying cosmic free. What do you mean by cosmic free?
Right. As I showed in the earlier plots, right? In the FORMOSAT 7 COSMIC 2, you have the observation at low latitudes, right? But for the FORMOSAT 3 COSMIC 1, you have observation in high latitudes. So I want to show where. Okay, I just need to go to that slide. So we still need to have the observation. Sorry, I just need to find it. Yeah. Okay, maybe. Yeah, this one. So yeah, you see here, most of observation of the FORMOSAT 7 are low latitude. But if you want to have a better low latitude, you really also need to know mid and high latitude. So I'm hoping that our successful latency of the FORMOSAT 3, FORMOSAT 7 radio occultation won't end at the second one, right? We need to continue. And it's not just only continuation, but also fill the gap between mid and high latitude.
Mm-hmm. Yeah, I think that you know in the talk by Vicky Zhu, she mentioned that this high latitude part of the observation had been filled by some commercial firms in flying a CubeSat or something.
Right, but still way far from enough.
Okay, great. Charles,
also,
I think we should go.
Yes, I have to go. Yeah. Okay, thank you so much. Thank you.
Okay, right.
All right, I get too much excited. See you guys.
Be careful. Try
okay.
carefully.
Okay, bye-bye.
Okay, everyone. Thank you so much for listening in. That this talk would end our today's session. This F7 and F8 online seminars, and we will plan another one perhaps in April. So please check your mail for announcement. Thank you so much.